Good morning, everybody. Welcome. Thank you for joining us. My name is Anthony Tosi, training manager here with Wales Darby, New York side of the business. My colleague, Rick Koester, is also on board. Good morning. And we will be enjoying about an hour plus of some information, hopefully. It's not brand new information. This is kind of a redo. I had 3 different topics tied into one, but the subject will be talking about lowering water temperature and still achieving some high efficiencies. Newer equipment is coming out and it only produces lower water temperatures with electrification and process, and things have changed, right? So just be aware you have options. So some of it might be scary. Hopefully today will be more of a refresher than, hey, I've never knew this before. Yeah. So Wales Darby is a manufacturer's rep. As you can see, we do have 2 locations covering quite a bit of the metropolitan, downstate New York State, out to New Jersey, all of Long Island as well. So pretty busy for hydronics. The city is a lot of steam, but oil, water-based, for many, many years, transitioning to, high efficiency, wall-mounted condensing. If there's gas, LP gases around us, certainly. Electrification now is in the works with New York City, and a majority of the state pushing a little bit of bashing on fossil fuels. Today is not about fuel. It's all about understanding systems and designing around efficiency, providing comfort. That's really what it comes down to. In this industry, if you want to call it, we are in the comfort and energy business, and what we can do for our customers and make a lot of money is a bonus, right? So people are getting smarter, doing their research. They're finding out about stuff that we need to be at least understanding, and not just putting the hand up and blocking it because it's just not our comfort level. So this next screen, I thought this was kind of powerful, just the word itself, right? So low temperature, like that might freak people out right there. High efficiency, right? That sounds like something that mounts on the wall. Doesn't mean it's guaranteed though, right? Hydronics is great. We love working with fluid or water, right? So very flexible, very manageable, understandable, repeatable. And now, with technologies, again, press fittings, it's just getting more and more cookie cutter approach. You just need to have that approach to having something that's repeatable, understandable, and just knock it down, not to be overwhelmed by, a gazillion pumps on a wall, break one down, you understand how the system works, and then just repeat, and just keep moving along. But that word change, that is something that you're gonna have to want, for this to work. That word shouldn't be scary. That should be every day. So the word change in our industry is really, how do I make more money, right? And you need to change with it because it's going to pass you by. Technology is moving quite at a speed that maybe most people aren't comfortable. I don't have a lot of youth coming into this industry at all also. So, we're making money. I've been doing this for a while. I'm pretty comfortable and I'm set in my ways. You change a color of a product, I'm questioning why. So now I'm telling you about lowering water temperatures. No, I'm not going to do it. And you were going to fail because the new equipment that's going to be offered and maybe demanded, you're not going to want to play nice with it, and then you're going to screw it up. So, and if it's my product, yeah, I'm going to be very selective who's installing my stuff. So here's low temperature, high efficiency, pretty much the stuff that I hope to cover today. This gas thing, it still has the unknown, right? We think because it has a label of high efficiency, therefore it's going to do it just by itself, and that's not the case, right? So there's a couple of products up here. Some of them are air to water heat pumps, some of them just condensing boilers, and then we have electric boilers. And I just put some water temperatures near the appliance, right? So those are really what we want to understand. With some of the new technology, 120 is where we want to play. That means we're delivering 120-degree water out to the building, the home, the space. And if you're not comfortable with that, then we need to have a deeper dive discussion. The thing about the 180s, it doesn't mean it can't go any higher. It just seems to be the number everyone's comfortable with. Doesn't mean it can't go lower either. And the one thing about that lower right corner, that NTI boiler there, 180, that doesn't achieve efficiency until you have 130-degree returning water. So there's a story we're going to spin on that. Again, some of this is regurgitation from, God, at this point, it was like years gone by. You know, it seems like COVID and webinar. Yeah, right. It's like, you know, I don't know where we are, episodes, how many of these we've done. But yeah, that the truth about condensing gas and why it is engineered to be so efficient, it has to change in the way we approach to the install. All right, so we'll discuss a good bit of those. So just to kind of knock down what a condensing boiler looks like, obviously it's engineered, it's manufactured to be in an environment that when we have flue products that are saturated to collapse back to a liquid, that's that condensation that flows across all of that heat exchanger. And then we're left with the good stuff, that higher efficiency, that state of where we're condensing. And now we're playing up in the 90, 92, 93% maybe. Again, it's all about return water temperature, lowering the water temperature so that this piece of equipment that now has become everyday, but yet I never see outdoor sensors, nor do I see a wet condensate trap or, you know, a neutralizer. So, you know, it's nice that we have these things, and basically I think what drove this was the lack of space. We didn't really care about efficiency still. We didn't really care that they're paying for all that engineering to achieve this high efficiency. It's just engineered to do that. You need to make it do that when you apply it into your systems, okay? And that, again, is that lowering water temperatures. So yeah, we showed some pretty big numbers up there, AFUEs, right? Up in the 95% for the most of those. But most of them installed without an outdoor sensor, yeah, you're probably doing about 84%. Probably no better than oil. So this is that change, right? How do I make this work for me? Because who knows? If you ever work for an engineer and he's got a 3-year list of energy costs, then all of a sudden he's realizing he's no better off, and he spent a lot of money. He might start questioning why. And I hope you have the answers and understanding. So I don't want the phone call to ring and people, you know, complaining. We need to start understanding that word change again. I need to change the approach. I need to understand the envelope of the building. I need to understand what the heat loss requirements are, and then I apply my systems. Now, think about this. I'm not saying we can't be higher than the most efficient state, right? So if it starts at 130, okay, well, if I can design my design day for 130, that's such a small little portion of our heating systems, seasons rather. So imagine now it's somewhere in the 30s. Where I live, it's 12 degrees around here. That's my design day. How often does it do that? Less than 2%, and that's probably for hours. So now if I'm always floating in that 25 to 35 degrees, man, I can start lowering the water temperatures because my heat loss isn't as great as it would be for a 10 to 12 degree day. So therefore now the engineering and the control strategy and seeing outdoor temperature, right, it modulates this amazing piece of equipment. But no, we throw the outdoor sensor away and we just peg the high limit to 180 and we hope and pray. You know, basically there's a sticker and then the homeowner's buying in on it. Right. And we don't do any better than maybe what we picked off the floor.
Just curious, you know, with everybody joining us today, we got people all over the place. Where are you and what is your design tip?
Excellent. And also, please be aware, I know I'm just showing you guys copies of what we put in your handouts. So there are 5 handouts. I think the 5th one, I'm holding 4. The 5th one is probably, hopefully, our line sheet. So yeah, so Wales Darby has many, many lines. Obviously, I'm not here to make this a sales pitch as much as, you know, yeah, you're gonna see some equipment that we represent. You know, we're pretty comfortable and confident, and we're systems people. I'm not the cheap guy, you know, like, oh, buy this bottle of water because I'm 5 cents cheaper. I am packaging everything for a system to service you in the field, right? So that's the approach. One-stop shop. Comfort, build relationships, have decent manufacturers, and then all of a sudden we're building systems. And this all works through hopefully a partnered wholesaler, right? So things happen along the way, and sometimes it's out of control. But
That's crazy numbers coming up too.
yeah, where are we looking? Where are we from?
I think Eric beats everybody right now. We got Mr. Warney with us this morning.
Good morning. Good morning.
Minus 16 down in Minnesota.
Sure.
You can keep that, my friend.
Yeah, yeah.
It's 20-something degrees here, and I'm crying like a baby.
Wow.
Yeah, we got some zeros up in Rochester.
Very cool. Thank you, guys.
Numbers, so.
Thank you again for joining us. I know it's kind of early, maybe even parts west still.
Yeah.
It was early enough here on the East Coast as well. But again, just showing you this photo here, that's a stainless steel heat exchanger. You know, there's different manufacturers, different styles, but it's engineered to be in an environment of an acid. Basically, our flue gas products wanting to naturally leave, we're fan assisting it, but we want it so cool that at the point it doesn't get a chance to leave, because that's dollars. Think about that. Anything that's a byproduct of fuel, fossil fuel, is dollars spent. So now if I can have that and reclaim it, and now I'm even greater for the dollar I put in for energy use, okay? So this is it, capture the condensate, right? Savings over traditional atmospheric or non-condensing boilers can be substantial if condensing technology is designed and applied properly. And that's the biggest thing. We kind of just throw that out. We don't really want to know more than, hey, what's the dollar? How much? Oh, primary, secondary. Okay, I need a pump. You know, like, we want to focus and keeping it in the box. Keep it simple, stupid, right? And that's a shame because, well, I'll say this, and I've been saying this for a while, you can make a lot of money fixing other people's problems or other people's mistakes. So you have really good equipment here. You just got to rip it out and do it all over again. I've seen it many, many times. So condensing boils with modulating burners, right? That's the engineering. We have the ability to see the change of the load because of outdoor temperatures, and now I can fire downturn, right? So I'm using less, but still providing the comfort needed, right? So decreasing the return water temperature. A BTU is a BTU. I only need X amount of BTUs. Well, here you go. I don't need to beat it up and waste, and then it goes up the chimney or out the flue, right? So that picture really is showing you what the end result is of a design, something that's making sense, right? Well, with condensers, when I make domestic hot water, that's not good enough in my book.
Yeah.
You know, I want to see something in the 90% and not the low 80s. So just go back to oil then.
Yeah.
You know, for a floor-mounted atmospheric. So the truth is, capturing condensate, right? Sounds all good and well. It's like, yeah, first we need to understand how to produce it, right? And that's, again, that change. If you're not doing this or refuse to, look at it for whatever reason, well, you're going to be left in the dust. All right, so lower return water equals high efficiency. And that's the truth. We are not achieving the efficiencies that we see on a label on the piece of equipment that we mount on the wall. So it's 130. At that roughly 130 mark, that's when our flue products start to have the ability to collapse. They're going to go from a change of state from a vapor to a liquid, all right? So that latent energy is something we want to recapture. We're paying for the engineering. You know, the install has been done. This thing has been running, no steady state, it's high limit, short cycling even for what we see on the wall. So the return water causes moisture to condense out of the flue gas, which is the end goal, right? So I think one of the things are getting that 180 temperature out of our minds, you know, thinking that we can't do anything like with certain appliances or emitters rather, that we can't lower water temperatures, and we certainly can. So for the return water temperature determines condensing operation. So the lower you go, the better the opportunity to condense, and therefore your efficiencies always have to go up. Now the chart kind of here shows you that make or break, right? So right side of 130, it's non-condensing node, and the left side is condensing. But then we have what they call this dew point, and that's something we have to be aware of as well. So with this dew point, that's where we're going to see lowering water temperatures following a dew point line that we'll have to use a combustion analyzer, right? So as we have to change, so therefore maybe some of our techniques in setting up a boilers also will come, and that's using combustion analyzer. So the dew point there is really key. So I kind of like plotted this thing here a little bit. This is not my chart, but I added a couple things to it. Again, there's what we want. We want that wet condensing heat exchanger, right? That heavy stainless steel, something that was engineered, something we paid for, but yet we treat it like it's every cast iron boiler. Down on the low left, that's again just the changing of state. That's what we want to achieve by lowering water temperature or approaching that 130 and less. That's when we're going to reabsorb and take advantage of all of that collapsing flue products back to a liquid, crossing over that heat exchanger, leaving or reclaiming the BTUs that would normally leave. So again, the chart's a little similar to the one prior. You see the right, you see the left, condensing, non-condensing. You see inlet water temperatures down at the bottom, and I put a red arrow where it says 130 degrees. And then if you go up and you go up and meet the dew point and go over, you'll see the first red arrow there says low temperature 130 condensing, and we're sitting at, well, let's just call it 87%. Is it that? I don't know, it might be less. But if you go down to the next orange or gold arrow, it's like high temp 180 condensing / non-condensing natural gas, fossil fuel. And that's where we sit, because all the way to the right, if you follow that arrow where it hits the dew point line, yeah, you're sitting at that 160, 170, 180, right? So really, we're not achieving what maybe we believe the label is telling us we should get, and that's not the case at all. Now, where do we actually see those efficiencies of that high, 90s, right? So you go to that highest red arrow up there, says low temperature, 100-degree condensing, right? Now 100 degrees, now remember this, 130 returning water temperature, right? So that possibly means maybe we had a 150-degree set point with a delta T of 20, right? So, okay, that might be the extreme of, here's Eric out there with -16, right? And I'm just saying the analogy is that, remember, the return water temperatures after we exhausted the heat to the building. So if we're shooting for a 20-degree delta T, so 130 starts the condensing process. So yeah, maybe, yeah, the machine sees, hey, it's -16 or something, and therefore I need to ramp up and engage more heat, and it will do that if we allow it. But imagine I do have a system that now runs at 120-degree water. I've understood the envelope of the building. I did a heat loss. I sized my emitters to maybe be oversized so that when I give it low temperature water, it actually still emits the BTUs required. So now I have a 120 design, but yet I have a 20-degree delta T, and now my return water back to the appliance is 100 degrees. So imagine my brain is saying, oh, I live in 180, I live in 180. Now you tell me I need 120, or yet I have return water of 100. I'm out. People are turning off this webinar right now. They're afraid. They don't want to change. They're set in their ways. So, but if you look at that 100 degrees, you go up, dew point, go over to the left, and there maybe you're achieving what the sticker says on the appliance.
And I was gonna, to your point, I was just gonna make this, and Eric actually just brought it up, like you say how people are afraid of the 180 mark, but when you look at a radiant system, we're running at 100 degrees, 95 degrees, and like Eric said, at -16, they're running most of his radiant, he says, at under 95 degrees.
Yeah.
And that's
100%.
We do it at radiant, why can't we do it with anything else?
Absolutely, and I have slides to bring that up, that point exactly. It's a very true thing that we play tricks on our minds. Like we think the emitter determines that it only can be this water temperature, and that is not the case. But yet, like Eric's point, as I've shown in slides, and you'll see it later, like why is it okay here? Yeah. Really what it comes down to, surface area.
Yeah.
The more the surface area, the lower the water temperature, you still achieve the BTUs required. Remember, we deliver BTUs, not heat, not temperature, right? Temperature determines our emitter's output, and that's where we might have to play with why certain areas or certain temperatures are needed. But
I don't think it's so much the temperature everybody's afraid of. I think it's the work needed to do the heat loss to make sure that we we are providing the right amount of BTUs to the space. Because you do the load calc, you do a heat loss and a manual J, and the numbers don't lie, So
and there's fudge in there.
Exactly.
And there is extra. There is the pad there. You know what I mean? So here, just kind of showing you, yeah, if you're in the efficiency game, or if you think you're selling high efficiency, but you're not understanding what the other backstory, the true story, right? Lowering water temperature is, yeah, today might be day one for you.
Yeah.
So here it is, you know, that latent heat, the changing of a vapor to a liquid. And this is where we capture a good bit of BTUs that would be normally just leaving the building. So without understanding and achieving how do we get this thing to condense, well, all right, so here we go. Lowering water temperature starting at 130, the lower you go, the better the efficiency. We got that, right? So now we have this great liquid coming back, this condensing, collapsing flue product to a liquid crossing over our heat exchanger. And if you were to capture for, you know, in a bucket, let's say, just have it drip into a bucket, and it's 5-gallon bucket, well, 1 gallon is 8.33 pounds, right? And therefore, times 970 BTUs. When I'm having that change of state from a vapor to a gas, it releases energy, and there's that 970 BTUs. So having a pound of this condensate times 970, that's just about 8,000 BTUs worth that would be reclaimed. It's in our pocket again. It's not out in the atmosphere. So just take that to heart and thinking what that can do, you know, for your fuel consumption, right? And in your customers. And if that's what their end all goal is, or you need to achieve certain efficiencies, just buying the appliance doesn't get it done. You need to set up the system. All right. So, you know, what will maximize the rate of condensate, right? If anyone knows, and this is an opportunity just to kind of plug in, it's a quick little poll without being a poll. What will maximize the rate of condensate? Sorry, I wet my gullet. Hope everyone had a nice Thanksgiving. I killed the turkey. I killed the turkey. Oh my God, there's a story behind this story. It's kind of funny. I guarantee this. Backstory, new relationship, doing a deep fried turkey. Nobody's outside with me, so I'm in the house. Time gets by, oil spikes. I misjudged the weight at the time. Oof. I walked in, I go, I killed a turkey. I guarantee this, they will never ask me to cook again. I guarantee, don't even touch the barbecue. I'm sitting back with a cold beer. I'm happy.
You did it on purpose.
I did it. All right, so
You
what?
got some cold water, and there you go.
Yeah,
Right,
flue
low
gas,
return temps.
right? It's the flue gas, the dew point, right? So understanding when we're setting up this, the boiler, right? Okay, so a lot of manufacturers, they say how they test and they calibrate, and then they ship it to where it's got to go in the world, right? So now we have different air quality, we have sea level change, we have gas quality change, right? So now it's the due diligence of that installer, not just at the installation either, but maybe in tune-ups and all, to do what? You gotta read the manufacturer manual, right? The factory manual, right? Because in truth is the CO2, we cannot do it by eye. You can't feel a pipe and know. You gotta use an instrument called a combustion analyzer. And with that, that is gonna help us dial in with our minimum and maximum gas, right? Fire rating, setting up the burner to be within the parameters with a little bit of extra, right? We can't be spot on. We have to be realistic that air quality changes. There's certain factors that are just out of our control. So this is the means and the needs, and this is not just for modern day heating boilers, right? This is regardless of fuel, regardless of appliance. And, you know, it is the fact that if you're not comfortable with a combustion analyzer, well, you're not necessarily, one, achieving the efficiency, and two, you could be making a byproduct that could be dangerous as well. So we have CO2, and we have carbon monoxide. So, you know, we have the parameters to play nice, and there's that safety and the efficiency that we want to achieve within doing that. So every manufacturer has their manual based on that particular model or that series. They'll show you what you need to set the gas valve up to, the firing rate and all that good stuff. So this is really something that I hope you have one. It is calibrated, right? It needs to be calibrated, and you understand what you're trying to achieve here, all right? So again, the dew point, right? We mentioned about the dew point, and the dew point is, listen, I have this range here, and I'm focusing on that 8 to 10, the red line, green line, and you see that swooping red, the dew point line there. So you can have a high dew point setting, but you're not condensing until you get 130 and lower. So, and then if you go too low, now you're waiting to condense because you're setting your parameters maybe closer to that 8 line, okay? So therefore, I'm not gonna start condensing. I'm below 130, I'm below 127, I'm hitting 125, and I'm still not condensing because the way I set up my gas valve. So again, to the right, this is one of the manuals that I just grabbed this out of. You have natural gas, you have propane. They're talking about parameters between 8.7 and 9.7, okay? So therefore, you have that range, and they kind of give you a little, you know, it could be as, here I think it's saying as much as a 0.3 difference between the low fire and high fire. But, you know, just understanding what this is all trying to achieve for you is that we want to maximize as soon as we can, right? Achieving that 130 and less so that we start collapsing because of that dew point. That dew point now is driving the efficiencies higher and higher, as you saw in that early scale or early slide. All right, so lower CO2 equals lower dew point equals less condensation. So we're just waiting, we're getting colder, returning water, we're still not condensing. So therefore, you might want to shift within what the manufacturer recommends, okay? So higher CO2, higher dew point, more condensation, okay? So it's just it's a cooler approach to understanding the inner workings of what we're doing with the strategy on board, all right? Using outdoor temperature, monitoring our demands, return water temperature, and all this stuff is being driven, and the dew point will drive our efficiencies higher and higher, all right? So yeah, combustion analyzers, you know, get familiar. If you're not getting a seminar, hook up with the manufacturer. So here, less condensation means lower efficiency. And if you're in the efficiency game or you're mounting these things on the wall and thinking you're achieving, again, the sticker, right? The number on the sticker, you got to be cautious. So if you don't do this, you're not gonna do the right thing by your customer. All right, yeah, perfect combustion. In the world of what we need, air ratio to fuel, stoichiometric is, I think he was a guy, well, I think this is his name, believe it or not. Hey, Stoich. Yeah. So, you know, natural gas, not 11.9, again, propane 13.7, you can read this in 15.5 for number 2 fuel oil. The parts per 10 parts air to 1 part gas, and 25 you see there in square feet of air to US number 2 oil. So a lot of these things, yeah, I mean, we have it on paper, we can achieve it, but in reality, you know, the real world is there's so many factors that are gonna throw the mixture off, and therefore you might be sooting, you might be too rich, you might be too lean, you could be causing CO2, you know, carbon monoxide rather. So, you know, something like that, we have to understand the means of why we use a combustion analyzer, and we use that extra air. A little excess air goes a long way, so that when things aren't 100%, we still have safety. Really, it is about safety. You might be giving up a little bit of you know, efficiency, but the other side is a life safety factor, a life issue, right? So just be careful in understanding what we're trying to achieve with that extra or excess air. All right. So yeah, lots to do with getting it right and making high efficiency, right? First thing is I got to buy into lowering water temperature. Something that mounts on the wall, it says it's condensing and high efficiencies. Well, it doesn't really start until 130 and lower. All right. Do a heat loss. Again, we got to envelope over equipment. We have to understand what our requirements are, room by room, zone by zone, or even whole house. Don't get locked into an emitter determining your water temperature. How much of this emitter? Remember, surface area, right? Certainly, you can see the closely spaced T's and stuff like that. That's really what that's all about. It's just kind of wanting to bring out more than just hanging this thing on the wall and supply in and return out. That's been a long time gone. But combustion analyzers, lowering water temperature, yeah, you're doing much better than maybe maybe you've done in the past. Have any questions, let us know.
So,
All right, make or break right there. That's a good picture. I want that 8,000 BTUs back. How do I start to achieve that? Well, 130 and less. Return water to that piece of equipment. Make or break moment. So will lowering water temperatures be in your future? Comfort and high efficiency is possible. I promise you that. A BTU is a BTU. What do you need to deliver? And these are what we have options as emitters. Lowering water temperature, they still deliver high BTU outputs. We're all good. All right. So are you ready for 120-degree air to water heat pumps? Right? Because that's the next wave. This is what we're seeing. We have a manufacturer been working for, well, not been working for 25 years, but the last dozen years with air to water heat pumps. And people call them chillers, people call them heat pumps, but they, in heat, will only produce, respectfully, 120-degree water, right? And then what do we do with that? And how do we approach the envelope of the building to satisfy comfort? So I thought this was kind of cool. I was just dabbling a little bit. Constructive change offers the best method of avoiding destructive change. So, here's a man that probably everybody recognizes, Teddy Bear, right? Theodore Roosevelt, actually, he's Oyster Bay?
Oyster Bay?
Yeah, Oyster Bay. He's a local resident.
Horse statue right there in the middle of town.
Yeah, that's right. But I thought that was kind of cool to read that again. Constructive change, meaning you want to do it. I don't want you to have to be forced to do something. Get in now, get in early. The fear of being a guinea pig and being the first guy, and so. There was a thing I took off of the slide and it said, do you want to lead or do you want to follow? And then I said, it kind of looks a little shitty. So I decided to put a quote here, and I thought that was appropriate. So air to water heat pumps, what is the basis? Well, Mother Nature provides us heat energy even in cold outdoor temperatures. So with a piece of equipment, call it a condenser, call it a chiller, heat pump, whatever. We have air source. Those are very popular. And then we have this air to water. And air to water to me, man, makes a lot of sense because water will never change. The medium in which we deliver to our emitters, it will never change. So if Mother Nature provides us heat, even in, let's say, -degree temperatures, the technology we have in our equipment now through electrified compression, right, refrigerant, we now achieve some kind of really high efficiency, but the give up is lower water temperature. So the other side of the game is, well, we just got to marry what we can maximize 120, let's say, to maybe something that we've been doing for the last 60 years. Grossly oversizing all our emitters? Sure. So now we take advantage of the deficiency for the last 60 years. Because if we understand and learn, oh, you can't do anything less than 180 for baseboard, yeah, I call bullshit.
Yeah.
Flag on the play.
Yeah, that question came up already. Our friend Manson. Manson was asking, about having, like, his house was designed off of 180 degrees.
Was it designed?
House. Well, that's what I mentioned.
So you have very little emitters then.
Well, that's it. It's a lot of the times we find that we have more emitters in a space because we're following a wall, not so much the load calculation.
Building practice said wrap the house. If you're doing thin tube baseboard radiation, more times than not, it was just wrap the house. Outside wall gets baseboard. Pump the boiler. Bigger is better.
Yeah.
180.
It's, to his point, though, I mean, not every application is
Nope.
going to be okay with it, but that's where doing the proper load calculation, figuring out how many feet of baseboard we may have,
100%.
It's a whole other thing.
So not to get off target, but this air to water thing is just showing you electrification with technology, call it inverter technology, using some refrigerant that now is even absorbing in the -degree ambient and still producing heat energy. Upwards, as you can see, in the 250% efficient. You're dealing with other pieces of equipment that we're dealing with throwing away money, right? So if we go back to the other slide where we have the arrows, I mean, the oil, the the high temperature condensing, non-condensing in the 80s. For every dollar of energy, you're throwing away 18 cents. So now understanding lowering water temperatures, marrying it with emitters, and using something like maybe this air to water heat pump, but yet I'm producing 250% efficiencies. That sounds like a benefit to my wallet, right? And I'm not giving up comfort. And that's where, again, we sit, energy and comfort business, right? That's really where we're in. Well, what do you do for a living? I'm a plumber. I'm a heating guy. No, you're in energy and comfort, because that's what your customer really wants to hear. So these things are using electric. So we're talking about kilowatts, right? Kilowatt is a BTU, and I'll show you that in a moment. But we also have these things called COP, SEER ratings, HSPF, EERs, right? So these are showing you your energy dollar versus operation, right? Or your output. So COP is coefficient of performance, sometimes CP, just to reduce it again. But you can see we're upwards of COP of 1. Anything electric is of 1 COP. Electric water heater, what is the byproduct of our fuel? So there is no flue. So it's 100%. $1 of energy in, 1 unit of heat out. And the other side is 1 unit of energy in with any fossil fuel. And if I'm at 82%, well, then I'm losing a percentage still of the flue with the byproducts of, the equipment. So now electrification using refrigerant, even in the -degree temperatures outside, and still achieving 100% minimum, and then outward up to 250, 290, 2.9, COP of 2.9. It's achievable. Be understanding of the fine print. When you look at any of this stuff, right, I'm holding up, any of these manufacturers, they're all playing nice with maybe AHRI testings. So you have to understand what the parameters were at the time of their testing to show you these high, amazing numbers to buy in. And then we have to apply it to reality. So where are the real deep dive charts? I want to know what the BTU output is when it's 0 degrees outside. The chart you're showing me is at 46 degrees outside. That's not reality. So again, that word change, you're going to want to have to do this, and therefore sometimes be a little deeper diver into information trail. All right. So you can see this chart, a lot of lines going left and right, but it's showing you like basically in the green, that's the heat pump. That's where we're achieving those high efficiencies. As we go left to right on the bottom, so outdoor temperature. So at 20 degrees and going up, this piece of equipment is still producing almost 25,000 BTUs. Now, if you never do heat loss or understanding what a house requirements are, that's a good chunk of most people's homes. Right. So it's another thing to be said that I don't know if our modern day heating in our buildings will only have one source of heat. So I think redundancy and having first stage, second stage, whether it be low temperature and have this huge amount of our heating season, up in the 80, maybe 85% of our heating season, I don't need more than 120. But if I should, then I'll turn on that. And it might be the fossil fuel, piece of equipment that's been there for the last 10 years and has another 20 years just waiting to be used. So again, playing nice and switching over, having some ability to use a control strategy. When it gets this cold out, turn that on, turn me off, okay? So we have some really cool equipment coming up, and I'll show you some slides. So the chart, again, as it gets colder out, it says, okay, well, maybe we have a little bit of a hybrid. We'll do a little bit of this and a little bit of that, but at some point, maybe I'm gonna turn off the outdoor condenser, and then I'll just go full boiler, let's say, whatever can achieve that high temperature or the higher temperature needed to carry the load. So, this is the process in which and why we do what we do.
You think of that 25,000 BTUs you're talking about, like moving that's a 3/4 inch pipe, and you think of a piece of ductwork or something, you're gonna move 25,000 BTUs through. Just the space savings.
I haven't said it yet, but think about this. Okay, so what if we did a heat loss, and then we did room by room, and we figure out our emitters, and then we do zone by zone, and like what is the chance that all zones are calling all the time at the same time, right? So therefore, we're playing this shell game with BTUs. I have twice the size of a boiler or a source just in case, but yet never do I get more than half a load of the house calling at the same time. So now, it's just a matter of understanding how the inner workings of what the house really requires. I said this time and time again, if you're not a heat loss guy, do it for yourself. Be a believer when you see it for yourself. You're going to look at your house differently, your space differently. You're going to look at what the source is versus your emitters output are. And then you're going to hear the boiler short cycling this winter. And then you realize that's really not a good thing.
Right.
It's not a good thing. That's no steady state of efficiency. Now you're throwing energy dollars out the roof and you think it's fine because your house is warm.
Right.
Warm, hot, is it comfortable, right? Because comfort means more than just skin temperature. Noise, smell, sight, lighting, all those things are factors, right? So it's important to kind of have a better feel for what maybe your expectations of your customer wants.
Right? Even when you do the load calculation, you got to keep in mind too, when we keep talking about design temperature, like for us on Long Island right now, it's about 15 degrees, we're using right now. That's less than 2% of the year, like even these last couple of days, these are probably some of the colder days we're going to see in the winter, and it's 20-something degrees.
27.
Right? We're not even hitting our design temps, So we're talking about how many BTUs you need on a design day, but even then that's limited to 2%. I think we looked at some bin data for Long Island. It was like 78 hours last year we hit design temp, and that's overnight. By the time you wake up, temperature's already above that, So it's pretty wild once you do the math and you actually understand it.
So the factors of this, if we have a design day, and let's just say it's 10 degrees, and I want to maintain 70 in, so there's that spread there, right? But we are never really ever living at zero. It's just in case that we ever do. I want to have enough horsepower to satisfy the space. I get that. But do you think the BTUs for a 0 degree day would be the same when it's only 35 out? But yet the equipment that we're driving, the horse, right, has no idea what the outdoor temperature is. So it just goes off on a stupid air switch and a stupid water switch. And it just races from 0 to 100 every time there's a call. So that sits there and waits and energy lost and up the stack, or just short cycling, and you're killing controls, electrodes, overheating the heat exchanger. Again, anything that's high efficiency, what do I say, Rick?
High maintenance.
High maintenance. And if you don't do maintenance, then you're going to see short life of failure of heat exchangers, electrodes, blowers, all those factors of why. This really expensive stuff really isn't cutting it. Well, you got to read the manual. It also tells you have to do water quality and you have to do maintenance.
You triggered some good comments with the the smaller loads, not everything calling at the same time. So we got a lot of buffer tank comments coming up here. So
yeah,
I'll leave that for, you're going to get to that point.
We have some. We have some coming up. Yep.
I'll leave that for a few minutes.
We're at 23 of 65 slides if I'm lucky. If you're lucky. Yeah. All right. So really harvesting energy from the air, right? So think about this. Using modern technology, refrigerant-based, electrification, blah, 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 nothing less than 100% efficiency of COP01. We have the ability to absorb free energy from Mother Nature. 2 parts of Mother Nature versus 1 input of power, and then we get out 3 units of heat. So this is that, kind of like mind scrambling. What do you mean? It's -5 out. There's still heat energy in there? Yeah, under compression, moving that outside air across our coil with refrigerants, R410A, R32 soon, like all these factors have changed now, but the technology with inverter driving efficiency higher and higher, even as it gets colder out. And this is just talking about the heating side. Again, anything that we talk about, air source heat pump or air to water, is both summer and winter loads, okay? With a little bit more ... involved. We need to know our loads to make sure we don't oversize one more for the other season. All right, so harvesting Mother Nature is free energy, which is a bonus. We were talking about the buffer tank here. And if you see, this is just a kind of a snapshot or maybe what modern day heating could be for someone's home, right? So we have a lot of different emitters. We can use air, we can use a hydro coil as long as it's sized for a lower water temperature. Certainly have radiant involved here, and we have some really cool cabinets or even wall mounted, what looks like a mini split. That's not refrigerant, that's water. So these are factors of, wow, I didn't know we have the ability to take an emitter that I would think I would need baseboard, and now I can mount this thing high on the wall, like maybe a kitchen. One of the problems with a kitchen is they maximize all the wall space for cabinets. Well, a toe kick is not going to get it done. You know, the factor of dollars for radiant wasn't in the budget. So, well, what can I do, right? I need to put some heat in these people's, kitchen, or maybe even in their basements, get it off the ground. Maybe they're in the flood zone, so I do like that high wall all the way to the left in the photo. This is some neat stuff here. The outdoor unit, right? There's our heat pump. We have different ones we can offer, different sizes, but both heating and cooling, low temperature heating. The buffer tank really becomes our source for the building. That's the vessel, that's the storage. It's an open vessel. It's just 4 tappings at minimum, but there's 2 tappings for the outdoor source or heat pump, and then 2 tappings to feed anything inward to the building or the space. So we are really concerned about just maintaining the temperature in that tank, using that as a battery and drawing that down as we get calls from different zones, right? So then we have a lot of flexibility using different types of materials, whether you're a PEX guy, copper guy, fusion, I don't really know what you're doing, but we have the ability now to do quite a few unique applications, or we can go back to baseboard even. You can go to a hydro coil, up in the attic there's nothing more than what we use small duct high velocity with our SpacePak hydro coil, marrying it with a heat pump.
Just going back to that buffer tank, one of the comments, we talked about sizing them and stuff like that. And what's nice, I don't know if you're going to go in depth with that, but we kind of go over that when we go into the SpacePak, air to water, webinars we've done. But what's nice about the newer inverter air to water heat pumps, it gives us, because of their turn down now, it gives us a better ability to go with a smaller, buffer tank. But for me, I've always, like when I talk to my contractors, it's always, it's cheaper to store the BTUs than it is to make the BTUs. So if you have the space, the system volume might not need, the larger buffer tanks, but if you have the space, you're better off still, going with a larger tank and storing those BTUs instead of producing them. So,
yeah. Remember, if my concern is only maintaining temperature in that tank, as far as what's going to cost me energy, right? The majority is running that condenser or that the heat pump. So if I have more storage, I can keep drawing down that tank, and still satisfy the space, so that when I do turn on that, whatever source it may be, it could be a boiler. It could be a heat pump. It could be a majority of things. And so now that tank is really kind of, being drawn, being asked to work, the tank itself. So now I need to rebuild that storage back up. So I'm gonna have a longer runtime. My steady state of efficiency will be achieved, right? Instead of short cycling, that turn on, turn off. So yeah, if you have the space, as Rick was saying, it's cheaper to store than to produce BTUs. Here's a good snapshot of what the offering is on some, what we say residential, right? This is residential. You say chiller, you might think something larger, multiple tons, 20 tons, 30 tons, 50 tons, 100 tons, definitely metropolitan or New York City based on that kind of approach. But these are 3, 4, and 5 ton chillers, and they're monoblock, and we have splits now as well. So different approaches where you're touching refrigerant. Majority of these are sealed. You're not even touching the refrigerant, so you don't have to be a refrigerant guy. And that was some of the beauty about stepping into high efficiency, maybe in an existing clientele who's already hydronically based. Hey, they're coming to you and they want to get rid of this old dinosaur, but I'm like, hold on a second, don't just dismiss it. You might want to leave it. How about if we add something that it's going to carry the load, lower water temperature for a good chunk of your heating season, and then if only then we can turn on the boiler as backup, right? So this is the thing I said about earlier about having redundancy. Unless the space is a premium and they need to get rid of it, just be very cautious about just immediately saying it's got to go. That's all. All right. So this is a chart showing you what is 120 degree water, what we can do, what we can achieve. There's a lot of different pieces of emitters. All right. Our outputs are based on our loads, so we need to have that first, and then we go to what we want to design with. Right. Does it have to be high temperature? Maybe. Maybe it's a glass building. Maybe it's a glass building on stilts over the water. You know, like I have extremes of homes where I walk in, it's a flat ceiling, no insulation, you know, glass all around, and it's, you know, it's radiant. So, and then they were complaining because there was some, this particular job I'm thinking about, the thermostats around knee height behind doors. So they didn't want to see them. So I'm like, okay, in the sunlight too, you know, on the south side. So I wonder why the heat was off. Kind of funky stuff.
Before you go forward with this, you know, I knew this question was going to pop up at some point because we talked about, you mentioned the word refrigerant, right? So, you know, there was a concern, like what happens, you know, when there's a change, you know, in refrigerant by mandate. Well, with air to water, it doesn't matter. All your refrigerant's outdoors. So your mandates don't mean anything. It's a sealed system. There is no refrigerant indoors, and that's what makes it more attractive in my eyes, because where we are, you know, especially my coverage area, what, New York City, right? The 5 boroughs, you know, New York City, there's requirements now with this new R32 that it looks like most, you know, a few manufacturers are going with, where you can't have any more than 4 pounds, 4 ounces of refrigerant in a space, you know, larger, or at, I think it's 1,000 cubic feet, right? So it's a 10 by 10 room, 10 feet ceilings. It's a small little room, you know. So if there's more than 4.4 pounds of refrigerant that can get into that space, then you can't have it. You also got the fire department getting into the DOB now, where they don't want line sets run through hallways because of paths of egress, you know. So it's really limiting what we can do refrigerant-wise, and that's where having an air-to-water heat pump, it puts all your refrigerant. Now, we do have a split system, you know, that does have a unit inside, but it's so limited, you know, as far as the refrigerant concentration. It's not something we'll have to worry about, but you know, your standard monoblock, you know, design, meaning that everything is outdoors, you don't touch it. You don't charge the system. You don't play with it. In fact, you don't even need a refrigeration, a 608, you know, license. You don't need to have that. You know, the certification, I should say. You know, well, yeah, all you're worried about is the water. You know, so
Universal Hydronics formula.
Yeah, big fan of it.
Right.
For those reasons.
So if we have an outdoor unit that can produce X amount of BTUs, what is our load requirement? Let's call it the design day. And then we size our pumping and piping. The outdoor unit does have some flow minimums, so we have to be aware of the equipment's requirements, but that's where the buffer tank comes in, right? All I'm concerned about is pumping and piping to that outdoor unit from the buffer tank. And then from the buffer tank, consider the buffer tank what was once the indoor, the boiler. Right? So now we're storing this low temperature, you know, water, and then I'm just doing zoning, pumping and piping again inside the home from the buffer tank out. So, or in, I should say, okay? So just to reiterate what this slide is kind of showing you, it's water temperatures for having that 120 available water. What are my options for emitters? And there's quite a few. Certainly, again, redundancy might come into play, having more than one source, having something carry a majority of our heating season using maybe lower water temperatures. Radiant, if you're in a radiant business or you're thinking this is getting to be re-energized, which it has been here on Long Island for sure, why not do 120 degree water? You know, we asked earlier, what are the water temperatures that, you know, you could use for radiant? And I have a slide later, it's kind of offset to the conversation, but you'll see it again. So here's just kind of giving you a little splash. What these things look like, it's an outdoor box, it's a coil, it's a couple of fans, it's a compressor, you know, inverter technology using, you know, R410A at this point. They'll be changing to R32, as most manufacturers I'm aware of are doing. But yeah, 5 ton, 3 ton. And we have some pretty big efficiencies here and showing you even some of the COPs or whatever, but just be cautious. Again, what was the COP achieved at for testing or during testing, right? It doesn't make sometimes reality check, right? So max heating capacity, here's a 3 ton, so BTUs an hour is 38,755. And again, that's 120 degree water. That's a good chunk, if not most of people's homes. You know, we don't realize or trust the numbers. It sounds too small, right? So we want to go bigger, 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 bigger. So just be aware until you do one or understand for your own home. You know, here it is, heating COP, asterisk. Be aware of what that asterisk means, that little star. It says here up to 5.01. Again, COP of 1 is 100%. COP of 5.01 is over 500% efficient. At what temperature, right? So if you go down below, ambient temperature, dry bulb, wet bulb, 45, 43. Is that ambient? And an entering return water temperature, entering returning water temperature of 86. So is that a reality of an application that you're going to do? So be understanding, anything electric is already 100% efficient, 120-degree water, okay? So if we are achieving somewhere in the 2 COPs, between 2 and 3, you're understanding the benefit of lowering water temperature, high efficiency right there. That's it. We can all go home now. We're done, right? So it's really something, again, that word is very powerful, change. Do you want to do the change? Do you want to be in that game? The change game makes money.
Right. Here's
the 60 or the 5 ton. Again, you can see that higher up the BTUs, upwards of 70,666 BTUs. Again, COP here is only upwards of 4.67, but the reality is at what testing parameters. Now apply that to reality in everyday living, and now maybe you back down into the 2s, again, 2 to 3 COP or 200 to 300% efficient, all right? Again, lowering water temperature, high efficiency. So this is what it looks like if you want to break it down. Again, we have this outdoor thing called the chiller, and we have this buffer tank. That outdoor unit is only concerned about maintaining temperature in that buffer tank. At what mode is being called? Because I can switch from heating to cooling in about 40 seconds. You know, that tank will start to change from a hot tank to a cold tank. Now we have pretty creative pumping and piping engineers, and we could do a separate tank, and we could do a bypass valve. You know, there are ways to have both heating and cooling at the same time, right? So a matter of that buffer tank, as we said, cheaper to store BTUs than to produce BTUs. So be aware, that's basically what we're talking about. Sealed refrigerant, electric-based compression, producing really hot gases that transfer into water, storing that in a buffer tank, and then using that buffer tank to satisfy the loads, the zone, the building envelope, okay? Making people comfortable. That's the game. All right, this is our split. We won't be bringing water. Let me just back up here, and I just want to say at this particular point, if you notice, that outdoor unit will be out in the ambient, and it could be quite cold. So we are bringing water outside, okay? Now, I don't know how you feel about glycol, and if you really understand the mixture or ratio of glycol, we probably wouldn't need more than 30% mixture here, okay? We could probably do it with less. I'll just go with 30, but people don't trust it. They take full concentrate, they dump it, they fill up the whole system. It changes your pump performance, it changes your heat transfer rate. So please understanding, again, that word change the way you look at things. Don't take it for word of mouth at the counter and trusting the guy who maybe doesn't really know all the truths, right? Maybe he's a parrot, maybe he's just repeating what he heard. So do your due diligence and look a little deeper into finding out this information. So yes, glycol might be in play here, okay? So be aware. Now when we go to this one, we're bringing refrigerant, as Rick said, inside the building. Roughly about 35 feet is our max. I guess if there's a leak, I don't know how much refrigerant we're holding in an outdoor unit, but that is a 4-ton. This is a 4-ton split. Really, you don't need to understand refrigerant.
Oh, no, this one you're running, you got a line set there, 25 feet of line set, so you're gonna be hooking up there.
It's 25.
25 feet is what it comes with the line set, it comes with the control cable. Do gotta run a little bit. It says no water glycol mix, but that's really, there's nothing outside. Right. We still wanna run at minimum of 10 to 15% glycol. just because it's not so much, we're not worried about outdoor, obviously, but you do have a refrigerant to water heat exchanger inside that indoor unit where there is a possibility with the lower refrigerant temps,
Right.
you could freeze the water in a heat exchanger. So that's what we're trying to avoid there.
Yeah, you're approaching those thresholds of cold water potentially freezing the indoor unit's heat exchanger.
Yeah.
So,
And Jeff, they are not pre-charged line sets. This is not Mr. Cool, my friend.
oh my God.
You're killing us, man.
All right, so this is what the split could look like. Again, line sets coming from outdoor to indoor. We have our magic box or module or SIS. You can see our pumping to a buffer tank. Look halfway between the buffer tank, there is a boiler, right? So again, if the house load requires something higher, if that ever it gets cold enough out, 120 doesn't get it done, well, we can just turn on a boiler. We can turn on multiple things, okay? And that buffer tank again becomes a source for all things internal. This is a good snapshot of what a split system looks like. There's a lot of pumping and piping going on here. There's a buffer tank or expansion tank, a lot of zones here with circulators. Nothing's insulated, so it leads to believe that this is for heat only, unless they're going to come back and insulate all and everything exposed. Because if this was a reversing cycle cooling to heating, it's going to be a swimming pool on that floor. So just be aware when you are using a chiller or heat pump for cooling in warm ambient air, Mother Nature takes over and condensation will form. Just be cautious. But if you look at that magic box to the left, the line sets are down near the bottom. They go up to the roof and it looks like they go towards the back of the pitcher. And then the copper comes up and over and we do our, I guess it would be our primary secondary. I don't see if I need to look right now. It should be, well, it's going to the buffer tank rather. That's what becomes primary secondary. The buffer tank becomes our separation from source to system. Here's some other photos, indoor and outdoor, getting it off the ground. Again, free air is everything for anything that needs airflow across a coil. Defrost, drainage, icing, good storage here in that other picture. And then obviously we're doing low temperature again. So if you have applications where low temperature is an option, it can take in and consider some other source besides maybe a wall-mounted boiler. Cold climates we're not afraid of. Again, envelope over equipment. What is the load? Let's figure that out first, and then we marry it with emitters that allow low water temperature to achieve comfort. All right, it's electric. Boogie, woogie, woogie, right? We all know the electric slide. You've been to a wedding. I dread that song. But here we go, and more, right? So we're talking about electric now, electric boilers, imagine. Again, anything electric, minimum 100%. But then we have more, the NorAir. NorAir is a product out of Minnesota. These guys are Monticello, Minnesota, and they're Electro Industries. A small company, but they do pack a big punch with anything electric, comfort, indoor air quality, makeup air, so forth. Electric around here is expensive, so I was a little bit of dragging my feet and thinking, why would we ever do this? And then application after application and learning, wow, there's some cool things about electric boilers. One, they get small. They get to loads that make sense. Sometimes even a turn down on a boiler, right? Again, I talked about this thing that hangs on the wall, and we think it's 96% because the tag says so, but you don't hook up an outdoor sensor, or you don't, do the combustion analyzer, or set up the parameters of lowering water temperature, achieving high efficiencies, right? So at best, maybe you're doing 82. I have electric boilers, 1 kilowatt. You want to buy a mini boiler, 1 kilowatt? That's 3,413 BTUs. I have a small bathroom. I want to do radiant, hydro radiant, right? So no fan, no noise, no primary, secondary, supply in, return, supply out, return in. We have this NorAir on the left-hand side. This is another option. You pick and choose your heat pump, non-communicative. It's just a signal. And then you pick and choose where we now have refrigerant going across a heat exchanger or a coaxial heat exchanger that does heat transfer, hot gases to water. Remember I said anything electric is 100%. These are upwards of 250 to 300 percent, COP of 2.5, 2.9, and so forth. So pretty powerful stuff here, giving you the options to pick whatever one you want to deal with heat pump outside wise. But they also do a nice add-on if they have the option, because let's be realistic, refrigerant, we're going to run out of BTU capacity. And now what do? I ripped out the boiler, right? Space was a premium. So now I can actually buy one of these magic Norairs with or without an electric BTU, electric boiler inside. So that will only come on when, if needed, or fully take over, or play nice as a hybrid in between. In addition, if the boiler was still there, you have now redundancy, fuel choices, and also serviceability if you should need during some kind of crisis in the middle of the winter. So we have the refrigerant-based outdoor heat pump doing its job for 80 some odd 90% of our heating load. Hey, just in case it gets a little too cold out, just pump that electric boiler a little bit, just charge, boost the water temperature. Hey, it's getting so cold out, turn off the condenser and now go full boiler. Or I don't want to buy this. I have something on the floor. I got plenty of life left. Buy the Norair without the boiler. Use that fossil fuel now and off and go. Again, redundancy. I think it's going to be the future of modern day heating. So here's a picture of what you can expect. You know, again, low temperature. If you need high temperature, turn on the boiler, right? Coaxial heat exchanger. One side of that inner tube is refrigerant. The other side is the water. And there's our heat exchange, upwards of 200% efficient. Here's a chart again showing you from right to left now, lowering outdoor temperature, what we can maintain with just refrigerant based, and then only then needed boost up, and then maybe full boiler only later. That's like 5 degrees outside. So, you know, for us around here, this is really starting to make sense for a lot of my already existing hydronic systems, especially with Radiant. Yeah. And these are the charts. Again, you got to look a little deeper. You got to see what these things really are based on testing wise. They're showing you amazing outputs of efficiencies and also the BTUs. So bring it back to reality now, put it into our numbers, and then really decide if this makes sense for your application. But I promise you, anything electric has no byproducts of fuel of flue, so therefore it will be 100% efficient at best. Or minimum, I should say, not at best. So talking on the electric side, using hydronics now, maybe the cold appliance, maybe a customer's just, I want to get rid of fossil fuel. I've had this a couple of times already. Contractors calling me saying, Ant, I have a customer, they want to get rid of their fossil fuel. What can you do? I heard you have something you can help me with. And all of a sudden I'm like, okay, well, let's do a load calc. What size boiler do you have? Oh, I need 140,000 BTUs. Really? For that size home that you told me you had, like, you know, are you heating the neighbor and the neighbor behind them? Because in theory, unless we do a heat loss, if in an existing home, chances are the electrical panel will not handle this new piece of equipment, all electric, for 140,000 BTUs worth. Let's turn around, do an example, do a heat loss. Well, you only need 60,000 BTUs, not 140,000. Now let's go back to the panel. Can we support, double breakers, maybe 2 60 amp breakers, or a 60 and a 45 amp breaker, because the 145 was 225,000 amp breakers. So there is a little bit of knowing, walking through the demand. I want. Well, can the house carry? Is it a new construction? Are they providing provisions for that 140,000? But if you really crunch the numbers and do a heat loss, you'll find it's probably half of that. It's much smaller. So it makes sense for retrofitting. Even if we want to do partial load, again, maybe we add this because they have PV solar on their roofs. So imagine you're producing electricity and you're just offsetting back to the grid, and you're never taking advantage of all that you've installed on your roof line. It's for the benefit of everyone else, and you're only seeing a small portion of the benefit. So imagine now I'm going to take advantage of everything that I can produce, and then I'm going to use it for me. And that's where this electric boiler for my home comfort comes into play. okay? I don't know if we're there yet with storing, for ourselves and being independent. It seems that locally, everything where I live is going back to the grid and just offsetting your monthly. But sometimes you produce way more than you utilize, and then they send you a nice little gift, but it's only a fraction of kilowatt dollars to what you pay using. So now you can use something to your benefit. It's called an electric EZB or electric boiler. Neat stuff here. So kilowatts, some new term, right? Kilowatts, it's electric, right? Boogie, boogie, woogie, and all that stuff there. But the idea is 1 kilowatt is 3,413 BTUs. So do the math there. You have 20 kilowatts. That's 68,200 BTUs. Again, that's doing a heat loss.
It's a lot.
That is a lot.
Double my house.
Right, exactly. So depending on the space under demand. So just be aware of those options with electric as well. These slides are a little bit old. I haven't updated them, but this whole lineup of what Electro is offering with their standalone. This one is a packaged boiler, as you see in the photo. There are 4 connections, and I'm not here to harp, but man, think about the time savings, the labor savings. It's already packed. It's an appliance. You have a supply, you have a return. There's 2 connections. You have a relief valve. There's your 3rd connection. The 4th connection is your pressure reducing valve. It's the only thing that does not come in the box. So you buy it based off of kilowatts. It's packaged. It's got this primary circulator. There is no primary secondary needed. Can it be? Yes, it can. Expansion tank, all things above. We have the disconnect in here. You have some high limits. You have your electrodes. I'm sorry, your emitters. I'm sorry, elements rather. Get a little tongue-tied with that word, but nice piece of equipment here. You can buy it single zone, 4 zone. You can buy it a digital touchscreen controller versus maybe analog, more watered down, price point driven. Neat stuff. But then you go into what you're going to build, right? So the one was packaged, and this is what you're going to build. This would be more traditional. You can actually piggyback this to any existing maybe boiler. You bring the return of the system, flow through, and then out into and back to the return of the boiler. Maybe they added an addition. Maybe they want a redundancy. I want to choose when to use one over the other. The cost factor. Wow, the fuel cost went up. My electric is low. I'll use this. And then I have the ability to switch. I can just flip a switch on the electric, use electric or bypass. This is basically an open vessel. There is no pressure drop. There is no coil in there. And you just pick and choose based off of BTUs required or what maybe your panel can handle. So many, many choices here when looking at this from different angles, right? So there it is, a kilowatt equals BTU an hour, 3412.003, or in Dennis Schrammel's world, 3413.
Wish he was listening.
Yeah, have a nice story about him. So here we go, bigger and bigger. We can go up to 27 kW, we can go up to 54 kW, we can go up to 300 kW, and most of these cabinets are going to increase capacity. So same size footprint, but now going from 1 to I think 16 kW at that first size, and then going up to like 27 or 28 with here. And as we're going to collapse a little bit of SKUs, but yet gain more capacity by adding more to the vessel. And I believe this one here is 1 million, and they're going to go upwards to 2 million. Can you imagine? So yeah, this is pretty wild stuff to think about powering this thing, right? But what's the byproduct here? There's no flue. There's no need for gas, no need for primary, secondary, no need for really maintenance or,
Water quality. That's it.
Yeah, water quality, again, is always going to be around us. Be cautious of water quality, right? So we want to create a low temperature system, right? This is the goal. How do I approach this thing? Where does it all start? We got to do a heat loss. What is the envelope of the building require? We have manual J, we have all these factors of what we need to understand, and don't overthink this. It's not that hard. We have programs, software, go manual, right? So basically what I want is somehow to understand living in your own home. I have no clue if my source make sense for the load, or my emitters make sense for the load, right? So you can do a quick calc and go around the room and measure all your baseboard, and if it's standard, let's call it slant in 30. We can figure out an output of BTUs per foot, and then go back to the boiler, like, wow, I have 3 times the amount of emitter BTU output versus my boiler, which could happen. The boiler's already double the size you need for the load of the house. That's what you want to figure out. That's where you really want to put the pen to paper, do a heat loss, and figure what the envelope requires. Then you go to the source, and you go, wow, that is grossly oversized. And then you go to the emitters, and again, that's grossly oversized. So that tells me one of 2 things. Either get the tin snip out and start cutting fins off, or I'm going to take this perfectly good cast iron boiler out, and do something different. Like, well, let's start playing with lowering water temperature. With non-condensing pieces of equipment, cast iron, we have a threshold no lower than 140. I don't want to condense in a non-condensing piece of equipment, all right? So, but 180 to 140, if I'm just pegging the 180 all the time and I'm wasting fuel and it's leaving the building and not going into my pocket or my comfort, right? That's a waste. So the idea is like, wow, if my emitters are more surface area than needed, let's look at a chart. Let's look at a chart and it tells me, right, how many BTUs per foot with 140. And then all of a sudden I realize I'm still carrying the load of the house. So therefore I'm not going anything higher than 140, 150 maybe. I don't have to go to 180 anymore. The short cycling reduces. Comfort level is better. My efficiencies go up a little bit. Certainly my fuel energy dollars is working in my benefit. So reducing heat loss and energy consumption, right? So again, the envelope, the importance of really tightening up the envelope. That might not be in our wheelhouse, that might be for someone else, but for yourselves and living in your own homes, your own environment, or making suggestions, right, to your potential customers. Now, maybe you partner with an energy guy or a spray foam guy or just an insulation guy, right? And you guys work together. One hand washes the other. But the idea is if we start understanding the envelope and reducing the load, therefore our heat output gets less, therefore our energy dollars get less, and then our efficiencies and comforts should go up. All right, so it has to start with what is a BTU? Well, it's a British thermal unit. It's basically energy required to raise the temperature of 1 pound of water at sea level, 1 degree Fahrenheit, right? So BTU is a BTU regardless of cooling or heating. What is the building's heat loss, or what is the building's heat gain? Warm goes to cool, right? So that's the envelope where I'm heating the space against really cold outside air. I'm going to lose my heat energy outward of the building. In the summertime, I'm trying to maintain a cooler temperature against outdoor ambient, so therefore outdoor ambient winds, warm always goes to cool. So this was a joke, it was an old slide I built because it was, again, we think we need 180, 180, 180. It's not the case. Really understanding, is it necessary? Yeah, it depends. What's the BTU requirements, right? So how hot was a kilowatt was a joke, right? Kilowatt's not heat, it's the amount of energy, right? So there it is, 3,413 BTUs. 1 kW is 3,413 BTUs. Associating with tons for refrigerant, right? 1 ton of refrigerant equals 12,000 BTUs. There's nothing about temperature here. We determine what temperature is needed based off of our emitter's output, how much surface area, okay? So therefore now it goes back to, I need to deliver X amount of BTUs, or in terms, maybe kilowatts, okay? So if we did a load calc, right, big or small, right, what is the load? Big or small, what is the load? We have the ability to do programming, we have manual J's, we have a lot of different information that we can get involved with and do room by room, zone by zone. And then we do the whole space, the whole house. That's how we determine at best judgment what our source would be. what is our source? What's our boiler? What's our heat pump? Air source, air to water, geothermal even, like there's so many factors of just electric baseboard, air to water, again, we can do the NOR air, but big or small, it's not just throwing a cookie cut BTU per square foot. It could get you in trouble. You could be oversizing, you could be short cycling, no steady state of efficiency. And
we had a conversation before with the gentleman, talking about the load calc and stuff like that, and he made a good point. We always talk about our side, right? The heating of a home and cooling of a home and all of that. But, when we talk about high efficiency, we're not talking, or at least bringing up weatherization. You got this home that's been leaking air like crazy. We want to have that high efficiency conversation, but we're still going to lose all the BTUs in the same spot.
Yeah.
Like it makes no sense. It's like, I want to buy a Ferrari, but give me the Honda Civic engine.
Put 86 grade gas fuel.
Right. So, if we're talking high efficiency, we really, these heat pumps, if you want to make them, and I think we've had those conversations where, all right, the heat pump can't give us enough BTUs. Now we got to put second, third, 3 units out there. It's going to price us off the job. Well, let's have a conversation on weatherization with the rebates we have out there today for the utilities. That homeowner can tighten up that house and drop 20,000 BTUs off that load, now we're talking, so the conversation's got to go both ways. The load is great, but understanding where we're losing it is key.
I think the reality is the lack of understanding, the lack of educating or knowledge of what we're actually installing versus what's needed. We got into the bigger is better approach for many, many years. I'm going to say 50 years. I think since the 70s or whatever, the building boom, baseboard became the go-to, and then what size boiler? Oh, well, you need a 4-section. No, it's just, you can't get small enough. And then the technology changed where we had some condensing, high efficiency, weather responsive maybe, but the turn down really wasn't there. But then we didn't trust it, so we still pegged 180. So now we went to more technology and better turn downs, and then we throw away the outdoor sensors. So we're not taking advantage of anything that we're paying engineering wise, just because of the latest and greatest.
I like Jeff's comment, hard to work on a house that uses latex paint as the vapor barrier. I'm stealing that, my friend.
I like that.
I'll give you credit anytime I use it, but I'm taking it.
So this went back to an earlier portion. Again, my slides are out of sync of the conversation, but what comes to mind when you hear low temperature heating, right? We're always comfortable with lowering water temperatures for radiant, right? And what is those temperatures? You can say, we could do 110, 120, 130, no problem, right? It's okay here, but anywhere else, it's got to be 180, right? And that just seems to be the fear factor, the horse blinders, right? So, just please be aware, if you do a room by room, look at the emitters, really determine what the room's requirement is. Again, centralized slip at 15-degree outdoor temperature, it only requires 4,000 BTUs. But they have more baseboard in there. It's close to 9,000 BTUs because of using 590 BTUs per lineal foot at 180-degree water. So if I use a chart here, and I realize, I'm not getting it done. I'm killing the 1 room out of 10 rooms of this house. Therefore, everything is bigger is better. But I want to go lower water temperature. I want to achieve better, greater state of efficiency. Energy dollars in my pocket, not leaving. This is a baseboard spec sheet, a chart showing you it's not just 180. Again, they give you that 590 at 180. That's great, but that doesn't mean I get nothing else when I do 150, 140. So I did the math here, and you can see in green, using 130-degree water with 15 feet of baseboard, I'm still producing over 4,000 BTUs for a 15-degree design day. I only need 4,000 when it's 15 degrees out. What do I need when it's 35 out, though? Half between, 0 and 70 is 35. So if it was a 0-degree design day, going back to here in Concord, New Hampshire, well, there's 5,253 BTUs. That's what the space requires when it's 0 out. What do I need when it's 30 out? What do I need when it's 25 out? I promise you it's not 52,000 or 5,200 BTUs, all right? So again, using the technology and outdoor weather responsive equipment will monitor and then change its firing rate. But don't think, because the emitter has been baseboard, it's always been 180, that it has to be. I can't do anything other. And that's not the truth, right? How low can you go? It says right here, it's all about surface area. Surface area equals more BTUs. With more BTUs, lowering water temperature is possible. Lower water temperature equals condensing and high efficiency. Marry the emitter back to the source, marry the source output to what the envelope really requires. Design day is key, but we're so rarely there. We're so rarely at that extreme of cold, right? Can we get there? Can we get colder? Yes, you can. So bigger isn't always better, right? And the value of the dime versus the nickel, it's so powerful as a visual to see that. I'd rather have a stack of dimes than a stack of nickels. Bigger isn't always better. Low water temperature doesn't mean low BTUs. It's all about surface area, right? Bigger here, oversizing more of it than required allows us now to lower water temperature. All right, here's again charts showing you it's not only 180, right? It's less water temperature, less BTU output, but I have more surface area, so therefore I equalize what the envelope requirements are. Again, manufacturers have even went to the extreme. So if I look at this chart at 130, the lower one, it says 1 GPM, 240 BTUs. Go to this one, 120, 1 GPM, 312. So if it is baseboard and it is a lack of wall space, we do have low temperature, high output baseboard. All right, these things are around us, they're achievable. Investigate, speak to your wholesaler. All right, so again, lowering water temperature, marrying it with a high efficiency condensing piece of equipment like a boiler, 130 and less is where we want to start. So marry your emitters to that water temperature, achieve your BTUs required by your heat loss, way ahead of the game. Panel rags, been around us. Again, it's all about surface area. Charts here showing low water temperatures, big outputs of BTUs. Again, do it all day with radiant, more surface area. Think about the whole floor becomes the emitter. Therefore, low water temperature, right? 110, 120, 130 again. And then here's that high wall from SpacePak. We did a conversion. We were thinking about, okay, what was it?
Did we do it with this? Or, yeah, we did.
We did it with this heating. I think we did 120 degree water and said, well, 11,843. That model's like, how many feet of baseboard is that, right? And we came up like 60 something.
It was like, yeah, 19 feet of baseboard or something.
Was that right? I thought it was even more. But anyway, you just kind of do the analogy and you realize like this piece of really cool stuff here, you can put a zone valve, you can zone it, right? And all of a sudden now you can put this in a room. I don't have to have baseboard. Maybe it's like I say, a flood zone, a basement area, get it off the ground. You know, it comes with a remote control. It looks like a mini split, but it's hydronics, both heating or cooling if you choose to, depending on what the mode.
Did. So if you did 140 degrees of water on that HW15, the middle one there, at 140 degrees, so you get it 16,553.
Right.
That's going to convert to about 28 feet of baseboard.
So that's, you know, again, it's kind of neat to see. People don't want baseboard anymore. What can you offer, right? Well, how about something like this, right? So here's another thin wall. It's like a console, clear glass, nice display, you know, and they have different models here. Again, lowering water temperature, but high output BTUs. Well, wow, look at that. 9 o'clock. How are we doing? Any questions?
Good, man. A lot of comments, a lot of
You've
conversation.
been busy over there.
So, yeah, appreciate, you know, between Jeff, Eric, you know, a bunch of guys here. And so it's good having conversation, keep me busy and
Good.
sane.
Well, I do appreciate obviously hanging in there. And this morning, it's been a topic that I've been tapping into because of the new offering of equipment. And I have to try to, again, that change, right? Constantly reiterating, reinforcing, supporting by design for my local contractors why this can make sense. And in the electrified world, for me, it was that, man, I'm just not buying because the cost of what electric is for here on Long Island. But I said then, what doesn't cost expensive, right? What fuel isn't expensive? And therefore, I went to application, no flue. I have large areas on the east end of Long Island where the contractor has to go from the bowels of the home all the way up 3 stories to get to the roof line, because out there they don't want a plume of smoke off the side of their homes. It's the Hamptons, it's money. It's like, you know, their expectations, it can't be achieved sometimes. So I started talking about remote buildings and electric boilers and not trenching LP or putting tanks or, you know, like really cool stuff started clicking with this product line. And I was like, all right, I'm in. Application-based won over cost.
Yep.
And then efficiency, electric boiler, minimum 100%, you know, and they come in different sizes where we can get smaller and smaller and smaller. So you got to play back to the panel sometimes if it's not a new build.
Yeah, absolutely. Yeah, we had some good conversations, and Jeff, you make a good point too. And this is something, you know, we kind of talked about, you know, we represent many different manufacturers, and when we have these dew points or even humidity control, you know, we're talking about these tighter homes, and you know, even just the inverter equipment that's out there that we're seeing on the refrigerant side, you know, you might not get as great of humidity removal, you know, and that's a conversation and something to think of. And, you know, I definitely educate yourself if you're dealing with systems like that, because it is tough sometimes. And that's why, again, another reason why air to water, you know, with SpacePak and what we do with, you know, NorAir and Taco's System M and all that stuff, you know, being able to do chilled water cooling, right? The humidity removal with hydronic cooling is so much better, you know, than with refrigerant, you know, so that definitely helps with that.
Are we talking about radiant cooling?
Well, just not even radiant, you know, even like high velocity or the high wall, thin wall, stuff like that. You see that a lot. Space. So I got a question here. Oh, okay, I see what you're saying here. Just asking about, do we need expansion tank, air vent, stuff like that? I'll put a hydronic. Yeah, that's a standalone system. Talking about the thin wall. You know, that's the SpacePak thin wall unit. That's just like a panel rad basically with an ECM blower in it. You know, like so it's very quiet. We just put one on our display. We've been running around with it. So this is going to be your expansion tank and air elimination. All of that's going to be on your hydronic system. That's going to be.
It's a closed loop system. You would need expansion for sure.
Exactly. You know, but that should be your entire system. This is just going to be room by room, so you wouldn't need a separate one. It's not its own standalone system. It would go with your current hydronic system. This
is water-based, so it's just part of, like Rick is saying.
Yeah.
But just look at some of the information that's, you know, we don't even realize, like maybe, you know, I've had so many people in class and go, I had no idea about baseboard charts. You know, we have charts for boilers and they show 2 different outputs. Like, well, why boiler this, boiler that? Same model, 2 different outputs. Like, so again, there's that change, right? Change the way you look at information. Ask that next question, right? Change the way you want to look at your own next job. Because the achievability of high efficiency, if that's your game, you know, you advertise it in your letterhead, you advertise it on your trucks, high efficiency, you know, whatever it is, but you never really achieve it. I'm like, yeah, all right, you're a fugazi, you know, it's like a smoke and mirrors here. So how about we start understanding how to do this, even just start to approach the conversation, right? Because I'll tell you this. Customers, your homeowners, they're getting smarter. They're getting smarter because information is available.
I've heard John say this a couple of times. Our counterpart over in New Jersey, Mr. Resso, you know, the facts don't lie.
Right.
You know, and it's the numbers are there. You know, if you do the math, you know.
Right. So.
All right.
Thank you, gentlemen. Thank you all. If I should not speak with you, have a great end of 2023 and a healthy and prosperous 2024. It's right around the corner. Thank you all. It's been a great year.
Absolutely.
We will talk to you soon.
Thanks for joining us.